In this video, we're going to build upon what we've learned about in stoichiometry and look at, well, what happens if one reactant actually runs out before the other? How can we still understand what's going on and be able to do math with what's going to come out the other side? Because if we have something that takes two parts and one part just runs out way before the other, that does present a bit of a wrinkle on how to deal with things. In this video, we're going to see how we deal with those things in what we call focusing on a limiting reactant, how to do the math, and how to interpret your results and know a bit more about stoichiometry. Up till now, we've looked at stoichiometry in terms of really needing to track just one reactant. Basically, we've said that one reactant is present in a certain amount and the other is present in excess. But what if we have two real amounts, right? What if we know that we have 5 grams of this, 10 grams of that? How do we know what is going to be the amount that's actually formed? Because in reality, if we have 5 grams of this mixing with 10 grams of this, one of those two may limit the amount of product that's going to form. And that one is what we're going to call the limiting reactant. So basically, one is going to be completely used up, and that is the one that is going to determine how much we make, right? Whatever we run out of first, that determines our total amount of products. The other one is going to be present in excess, and that means some of it is going to be left over. So a great example of limiting reactant is, let's consider that we're making sandwiches, right? We have a sandwich which is made of 2 slices of bread and 1 slice of cheese. What if we have 28 slices of bread and 11 slices of cheese? And I hope you can see where I'm kind of going with this, right? That if we have this recipe and we have these ingredients, are we going to run out of cheese or bread first? That is going to be what determines how many sandwiches we make. And if we have this combination, we say, well, we'll actually make 11 sandwiches because we're going to run out of slices of cheese first. We'll need 22 slices of bread to make the 11 sandwiches. We'll use all 11 of the slices of cheese, and that means that we're going to have 6 slices of bread left over. This is exactly what we're doing when we deal with chemical reactions, but not in terms of bread and cheeses, of course. So how did we get this? How do we break it down a little more? Well, what we're really saying is, let's consider the bread and the cheese. If we were to imagine that we were limited by the bread, we would say it's 28 breads that we have. We make 1 sandwich for every 2 breads, and that means that this amount of bread, if unlimited by anything else, will make 14 sandwiches. What about the cheese? If we have 11 cheese, we need 1 cheese for 1 sandwich, and that means we make 11 sandwiches. So basically we're saying, well, given the amount of bread we have, how many sandwiches will we make? Given the amount of cheese, how many sandwiches will we make? And it turns out that bread is going to be our excess reactant because it's the one that could make more sandwiches. The cheese is going to be our limiting reactant. That's the one that is going to make the fewest number of sandwiches, and therefore what's going to run out first. So again, when we apply this to chemical reactions, it's the same thing with 2 different reactants. One reactant is going to run out first. That's what we want to determine. Let's take another look at an example here. Say we have 6H2 and 4Cl2, and after reaction we make a certain amount of HCl. What we can see by looking at this is that all of the chlorine has been used up. It's the limiting reactant. These 4 chlorines can make 8 HCl's. The 6 hydrogens could actually make more than that. And as a result, we have a couple of hydrogens that are remaining. The amount that remains is based on how much was used, right? In this case, we made 8 HCl's. That consumes 4 H2 hydrogen molecules. And therefore, the 6 that we started with, we now have 4 less, and there are 2 that are still there. Okay, let's take a look at a practice question. And here I would recommend you go ahead and pause the video and see if you can work through this one. If not, it's not a huge deal, start watching the video if you need to, but I would really challenge yourself to pause and see if you can come up with a good answer and at least see how far you can get. So pause the video now and we'll discuss in just a moment. All right, let's take a look at our answer. So first thing we're saying is, if we combine 4 molecules of hydrogen with 3 molecules of oxygen, which is limiting. And let's do the exact same approach we did with those breads and cheeses. Let's say, well, if the hydrogen is limiting, how much would we make? And here we have 4 H2s. We want to see that we get 2 waters for every 2 H2s that we use. And therefore, if the hydrogen is limiting, we're going to form 4 waters. Well, what if the oxygen is limiting, right? Well, we say it's 3 molecules of O2. We only need 1 to make 2 H2Os, and therefore 6 waters would be formed if it was the oxygen that was limiting. So in this case, which one is truly limiting? Well, the hydrogen creates less water, therefore it is going to be our limiting reactant. If we determine that oxygen is used in excess, this really doesn't have any meaning anymore. It's saying that, well, we could have, this is like in the sandwiches, we say we could have made 14 sandwiches, but we can't because we're limited by the cheese. And in the same way, these 3 oxygens could make 6 waters, but we just don't have enough hydrogen to make it. And so whatever we did here for the excess reactant is really not relevant anymore. So the next part of the question is saying, well, if we have this combination, 4 molecules hydrogen, 3 molecules of oxygen, how many waters do we actually form? And the answer here is that we're going to form based on the limiting reactant, and that's going to be 4 waters, right? The 6 isn't really relevant anymore. We definitely don't want to say it's 4 plus 6 is 10 waters. That would be very far from what we're going to form. We form based on whatever is limiting. Just like with the cheeses and the breads, we form 11 sandwiches in the end. We're limited based on whatever we run out of first. And the last question is saying how much of the excess remains, and this is the oxygen. We want to know, well, once we use up all the oxygen that we need, how much is left behind? And so that's the first thing you need to figure out here is how much oxygen did we use to make these 4 waters? And in this case, right, to make 4 waters, it takes 1 oxygen for 2 waters. So 2 oxygens were used. If we started with 3, that means that initially we had 3, 2 were consumed, 1 oxygen remains. That's the answer to this question of how much of the excess reactant, water in this case, is going to remain. All right, let's do one more practice problem. And this one really kind of takes us full circle. I would recommend you go ahead and pause the video here. This one I would say is pretty challenging, right? We want to make sure that we're recognizing some names of chemicals. We want to get a balanced chemical reaction, and then we want to do this limiting reactant stuff working in our stoichiometry. So this one could be, very challenging. So I would recommend that you pause, take your time, really try to get this one down on your own, and then we will discuss the video. All right, so if we look at this, we say we have 8 grams of sodium, 8 grams of chlorine. We're going to have a reaction that makes sodium chloride, and we want to know which one's limiting. And so the first thing is we absolutely need a balanced chemical reaction. And so for this, we should break it down. It's sodium and diatomic chlorine. This is how chlorine likes to be. And we're forming sodium chloride. Is this balanced is the first question, and the answer so far is no, it's not, that we don't have the same number of chlorines on each side. But we can see that if we double the sodium chloride, now the chlorines are good, there's 2 on each side, and then we need to double the sodium for that. And so this will be our balanced chemical reaction that we're going to use for the rest of this problem. Okay, so now we need to determine which reactant is limiting. And to do this, we want to say, well, how much product is each of these 2 reactants going to form? Basically, if I have 8 grams of sodium, how much could I form maximum? And if I have 8 grams of chlorine, how much could I form maximum? And while it may seem like, well, it's the same amount, so neither is limiting, remember that different amounts of mass are going to be required of for each reaction turnover. It's going to be based on moles. So to calculate the sodium, we'll set it up this way, right? 8 grams of sodium, we convert to moles of sodium, we convert to moles of sodium chloride, and then even to grams of sodium, right? We can determine moles, but we can just go ahead and determine grams too. And this says that 8 grams of sodium could potentially make 20.3 grams of sodium chloride. How about the chlorine? Well, here, 8 grams of chlorine, we convert it to moles of chlorine, we convert it to moles of sodium chloride, and then we convert it to grams of sodium chloride. That would make 13.2 grams. And so this is the results of either of these calculations, right? The sodium would make 20.3 grams of sodium chloride, the chlorine would make 13.2. And therefore, we would determine that it's the chlorine that's limited, right? Again, each of these calculations are imagining that the other is available in complete excess, but what we determine is that the chlorine is going to run out first. That's the one that we want to look at from here on out. If we want to say, well, how much sodium is left over, that would be based on making this 13.2 grams amount of sodium chloride. And again, that's the amount that's actually made. based on the limiting reactant, which is chlorine in the bottom calculation, we're going to make only 13.2 grams of when we take this mixture and bring them together.